Alright, this video is going to cover momentum. This is the second half of Unit 3. The big difference between momentum and the last video on energy is that momentum is a vector, which means you have to consider the direction. So if something is moving to the right, its momentum is pointing to the right. If something is moving up, its momentum is pointing up. Momentum is a vector, very important. Momentum has the units. It doesn't have a special unit. You just combine the unit for mass and velocity, so kilogram meter per second. Go ahead and give this first momentum question a try. Pause your video and then play the video after you've attempted the problem. Okay, you should have attempted this first problem. 3 objects are moving on a straight level path, and we have 3 position time graphs. Position time. The question's asking, in which graph does the momentum increase? So momentum equals mass times velocity. The mass is constant, so to find out if the momentum is increasing or decreasing, I need to know, is the velocity increasing or decreasing? So position time graph, I get the velocity from the slope. So here I have one slope, so I have a constant velocity, constant momentum. This one, I have a 0 slope, so 0 velocity, which means I have 0 momentum. But this third graph, if you look at the slope of the tangent lines, what you'll notice is that the slope is increasing. It's getting steeper and steeper and steeper. And so the velocity is increasing. If the velocity is increasing, then the momentum is increasing. So the answer is graph 3 only. Think back to the last review when we talked about work. Work is when a force moves a distance. Impulse is kind of similar to work, but instead of a force moving a distance, it's a force acting over a period of time. So when you have a force and a distance, there's work. When you have a force and a time, there's impulse. And we simply multiply the force and the time. If the time is longer, the force is smaller. So think about like an airbag in your car. If you get into a crash, that airbag inflates, and what that does is it makes the time that your head is colliding, it takes longer because it's a fluffy airbag. Long time, small force. If there were no airbag, your head would hit the car super fast. You'd have a short time and a big force. Another way to find the impulse is the area under a force-time graph. Impulse momentum theorem says that the impulse is equal to the change of momentum. Give the next problem a try. Go ahead and pause the video. Okay, a ball is initially at rest on the ground. Somebody comes and kicks the ball at an angle. So here's the kick. And they kick the ball at an angle of 60 degrees from the horizontal. And the ball moves with a speed of 5 meters per second. We want to know what's the impulse. So there's 2 ways to find impulse. I could multiply the force and the time, or I could set the impulse equal to the change of momentum. For this one, I'm going to choose change of momentum. So impulse equals final momentum minus initial momentum. The final momentum is mv. The initial momentum is mv naught. The initial velocity is 0, which means I have no initial momentum. So the impulse is just equal to the mass, 0.4, times the final velocity, 5 meters per second, or an impulse of 2 Newton seconds. Choice C. Conservation of momentum, kind of like conservation of energy. The idea is the same. The total momentum before is equal to the total momentum after. Okay, no matter what happens, maybe there's a collision, maybe there's an explosion, maybe two things stick together, but the total momentum of both of the objects before the collision or whatever happens is equal to the total momentum afterwards. That's what I mean by conservation of momentum. Here's the equation I use. Now, in any type of collision, the momentum is always conserved. It doesn't matter what kind of collision. They might bounce off of each other, they might stick together, maybe they explode apart. The total momentum is always conserved. However, the kinetic energy is not always conserved, so we have some different names for the collisions. The first type is called an elastic collision. That's when the kinetic energy is conserved. The second type is an inelastic collision. That's when the kinetic energy is not conserved. And that's what you should internalize, these two types of collisions. Now there's a third type that we call a perfectly inelastic collision. And all that means is that the kinetic energy is not conserved because it's inelastic, but the objects stick together. And that's what the perfectly is referencing. They stick together. After you've seen lots and lots of momentum problems, there's some key words you should look for. So here's the words that I've found in different momentum problems. Problems where you have train cars linking, coupling, locking, blocks sticking, anything about a collision, a bullet being stopped or embedded or slowed by another object, a spring compressed between two masses and released, a single object exploding apart, someone or something landing or falling off of a sled. What all these things have in common here is they all have to do with two objects and some sort of collision. So we're gonna end the second half of this review with 3 problems. Go ahead and pause your video now and attempt these 3 problems. Okay, you should have attempted all 3 of these momentum problems. First one, which of the following is true when an object of mass little m, so I have a little mass, is moving on a horizontal surface and hits a bigger mass, big M, and sticks to it. So little mass is moving on the surface, big mass isn't. They collide, and then little mass and big mass get stuck together, and we want to know which of these is true. So first of all, you should remember from a few minutes ago, when 2 objects stick together, it's called perfectly inelastic. So choice A, the collision is elastic, that's false. It's inelastic. Choice B, all the initial kinetic energy of the less massive object is lost. So that means that this small mass has to come to a stop. I don't think it's going to come to a stop if it sticks to the other object, so that's also false. They're going to go moving off together with some speed. The momentum of the objects that are stuck together has a smaller magnitude than the initial momentum of the less massive object. Well, if it had a smaller momentum, that means that we would have lost momentum. That is definitely false because momentum is always conserved. The speed of the objects that are stuck together will be less than the initial speed of the less massive object. So that's saying that after the collision, these 2 objects have a smaller speed than what this one started with. That sounds about right, because I'm thinking if I'm driving a little VW Beetle and I run into a big truck and I stick to it, after that collision I think we're going to be moving a little bit slower than before the collision. So that's sounding good, but let's read the last one. The direction of motion of the objects that are stuck together depends on whether the hit is a head-on collision. Let's go back to D. So at the beginning I have a small mass and some speed, v. Afterwards we stick together and we become one big mass. So the mass is now bigger, and for these two things to be equal, if I have a bigger mass, I need a smaller velocity. Bigger mass, smaller velocity. Definitely choice D. This problem is a pretty standard collision problem. We've got two railroad cars. The first one has a mass of 2,000 kilograms and it's moving at 10 meters per second. The second car, this is a flat car, has a mass of 3,000 kilograms and it's moving to the left at 5 meters per second. They collide and they couple together, which means they stick together. So again, we have another perfectly inelastic collision. And we want to know the final speed at the end. So I'm going to start with my conservation of momentum equation. M1 v1i plus M2 v2i equals M1 v1f plus M2 v2f. This is one of the few times in the year that I recommend that you just put the numbers in right away. So I'm going to plug in all my givens. The first mass is 2,000 and it's moving with a speed of 10 meters per second. The second mass is 3,000 and it's moving with a speed of 5 meters per second. But it's moving to the left, so I have to call that negative. Remember, momentum is a vector. Now at the end, since they couple together, both of their speeds are the same. So what I'm going to do is factor out that speed, Vf, and add the two masses up. 2,000 plus 3,000 kilograms. And I'm going to solve. So I have 20,000 plus a negative 15,000 equals 5,000 Vf. So 5,000 equals 5,000 Vf. So Vf equals 1 meter per second. Choice A. Okay, last problem, 2D momentum. Anytime you have a 2D momentum problem, so a common one would be like a billiard table or a pool table where the balls collide and now they can move in two dimensions. They can move forward and back and right to left. What we do is we just separate it into two one-dimensional problems. We separate it into a horizontal problem and a vertical problem, just like we did in projectile motion. And we remember that momentum is conserved in both of those problems, both the horizontal and the vertical. So let's try this. A stationary object explodes, breaking into three pieces, m, and 3m. Two pieces of mass m move off at right angles to each other, as shown in the diagram here. And we want to know what is the magnitude and direction of the velocity of the third piece that has a mass 3m. So here's what's happening in this problem. We have some object, maybe it's a rock. It has a mass of 5m. It's not moving at all. Its velocity is 0. So initially in the problem, the total momentum, initial momentum, is 0. And that's pretty important because momentum is conserved. So later in the problem, the momentum final has to always be 0. Okay. So what I'm going to do is here I have two momenta vectors of the first two objects, MV and MV. And that's a big V. And I'm going to add those up to get the momentum of both of those. Tip to tail, draw the resultant. And so that has a momentum of square root of 2 m big V. Okay. So this is the momenta, this is the momentum of the two smaller masses, square root of 2 mv. I know that the total momentum has to be 0. So the other mass, the third mass, which we've ignored up until now, has to cancel it out. So it has to move in the opposite direction, and it also has to have a momentum of square root of 2 m big V, so that the total momentum is 0. So right away I'm looking at the direction. This is good, this is good, this is good. So it's between B, D, and E. So the momentum of the third object has to equal square root of 2 mv, big V. And the equation for momentum is mv, but this mass is 3m. So 3m, I'll call this a different v, a little v, is equal to square root of 2 big V. And I'm solving for the speed of the third mass. So divide both sides by 3m. Cancel, cancel, cancel. And I get that the speed must be square root of 2 over 3 big V. Or choice D.